Deep learning with Python. Hello, everyone. My name is Dimitris, and as Susanna said, we will go through the second chapter. So we have lots of ground to cover, and it might take more than 1 hour, actually, around 1 hour and 15 minutes. So prepare yourself. The mathematical building blocks of neural networks. Let's see the contents of this chapter. So today we will see our first example of a neural network, the actual code. And we will build it, we will train it, we will see what tensors are and what tensor operations are, which are fundamental for deep learning. And we will also see how this whole thing works. So what is backpropagation that we mentioned in the first chapter, what is gradient descent, how this helps us to train the model. So let's start. First of all, let's have a look at the first neural network. As I mentioned before, we will train an image classifier. So the idea is that we will have images from MNIST datasets. Probably most of you are familiar with. It's the Hello World Play dataset for deep learning. And it consists of images of handwritten digits, as you can see here. So we have 28 by 28 pixel images. They are grayscale. And we have 60,000 of them for training and 10,000 for them for testing the model after we train. And of course, the goal is to classify the images into 10 categories. So it's 0, 1, 2, 3, up to 9, whatever it is. So we try to find the category, the level. Now, first of all, we have to get the data in order to train a model on the data. So the good thing is that MNIST comes with TensorFlow. The way to import it is from tensorflow.keras.datasets, import MNIST. In the future, we will see that some datasets we will have to download. It's a more difficult process. This one is very easy. Now, in order to get the actual data, the NumPy arrays, we call MNIST.loadData, and this method returns these two tuples. Each one has the images and the labels. So we have train images, train labels, test images, and test labels. Now let's see what these things are. First of all, train images, as I mentioned before, are these 28 by 28 pixel images. And with .shape, we can get the shape of this thing. We don't yet know, we haven't discussed about what this thing is. It is actually a tensor, a rank 3 tensor. But just think of it of 60,000 images, 28 by 28, as you can see here, okay? Then we will see the length of the train labels, how many labels we have. It should be equal to the images, so 60,000 images. And we will see what these labels look like. So these labels are just numbers. So for the first image, we have the number 5, for the second number 0, etc. So the idea is that we have one label of one number corresponding to one image. And now let's see also the test. So this was the train images and labels. These are the test images. We have 10,000 of them. So as expected, 10,000 by 28 by 28. The length is again 10,000. And let's see what they look like. So again, as before, we have a 7, 2, 1, etc. So all the numbers that correspond to the images. Now, let's see what will be the workflow. The idea is that we have the data. Now we will build a neural network. And then we will train the network using this trained data, so the images and the labels. And after we train it, we will evaluate the learning process using the test data. First of all, to train the network, we have to build it. And this is the way we build a network in Keras. The idea is that we use layers. So the model is nothing but, the neural network is nothing but layers connected to each other. So the building block of a neural network is a layer. And the layer is just something that takes some input, some data as input, and output some data, okay? And we hope that internally there is a new transformation that outputs a new representation that is more close to the final core. So a layer is just a filter of data, okay? Imagine it as something that takes data and filters the information we need and outputs something new. Let's see how to build one. So this is a very, very simple way to build a neural network in Keras. We import keras and layers. I hope you are familiar with importing a package in Python. And the idea is that this is one of the three ways to build a model in Keras, the sequential. So sequential is Keras.sequential returns a model that consists of layers that are stacked upon each other. So we just pass a list of layers and we get a model with these lists one after the other. And here we pass a list with two layers. The first one is a dense, and we will see what this means later on. And the second one is again a dense. This one outputs 512 numbers. This one outputs 10 numbers. You also see that we define something called activation. We will see in the next slides what this is. Important thing is that this, the activation of the last layer with the 10 outputs is softmax. This means that these 10 numbers that this layer will output, and thus the model will output, are probability scores. Because it's softmax, these numbers are probability scores, so 10 probability scores, which means that each one of these 10 numbers is between 0 and 1, and the sum is 1. This is what probabilities are. And this shows the probability that the image, the picture of the digit, belongs to one of the 10 classes. So we take 10 probabilities, and hopefully the one with the highest probability is the correct. Let's run it. So now we have built the model. That's simple. And after we build a model, before training it, we have to compile it in Keras. So compilation needs three things. One is the optimizer, which is a mechanism in order to update the model weights. We will see today how this works. The loss function, which as we mentioned at the previous chapter, is just a function that returns the difference between the predictions of the model and the targets. And because this number might not make any sense, we just want to minimize, we cannot interpret it always, we use sometimes metrics, which is a number that makes sense, that is measures the performance of the model. So this is how we compile a model. We call model.compile. And in this method, we use these three arguments. So optimizer will be something, RMS prop in this case. The loss will be loss categorical cross entropy. So cross entropy is just some kind of loss when we want to compare probabilities or information. Categorical is because we have 10 categories and only one is correct. It cannot be 2 or 3 things, one digit, it can be only one in this case. And sparse, it's because the targets are not actually probabilities. It's not one hot, it's just one number. Don't pay too much attention if you don't understand. It makes sense if you don't understand right now all these things. And for metrics, we will use accuracy. Accuracy is just what percentage of the images we predict correctly and what not. So this is how we compile the model. And now before training, one more step is data transformation. Usually we have to pre-process the data and that we will use for training and validation. This means that this is because the raw data usually are not in a form that is very friendly for the moment, for the model. In our case, the model consists of dense layers, which means that we have to flatten the data. So instead of feeding an image, we will feed just the information of the pixels. So instead of having 60,000 by 28 by 28, we will transform it to 60,000 by 28 times 28. So flatten again. And the second thing we will do is that since our current images, the pixels hold values from 0 to 255, the 8-bit usual unsigned integers, we will divide by 255 in order to get the numbers to be between 0 and 1. So the intensity, the grayscale, will be from 0 to 1 after that. Let's see how we will do this. This is the code. So we take each one of these NumPy arrays, the train images and the test images. And first of all, we reshape them to the new, we flatten them like this or like this. And the second thing is that we divide by 255. So now our data are ready to be fed to the model. Our model is already compiled. We just have to feed the model, which is another word to say train the model. So in order to train the model, we call model.feed. And in this method, we pass the training inputs, so the images in our case, and the targets, which are the labels. And we also define how many epochs. So epoch is, in this case, 5 epochs means that we will go through all the training data 5 times. And batch size is just a number because in Keras, we always feed batches, so chunks of data, not only one data point to the model, either for training or for evaluation or for prediction. This is how many batches, what it will be the size of the batch at each step. So 120 images per step for training. And if we execute this code, we see that the model starts training. It's very fast because it's a very simple, very small model, just 2 layers. And yet powerful. I mean, you see that, first of all, the loss for each epoch. So here you have the 5 epochs, starts quite high, 0.25, drops to 0.03637, which means that, first of all, it works, right? So the loss becomes smaller and the accuracy becomes big. So in the end, we have 98.9% accuracy in this dataset. And that was it. So just in 4 or 5 minutes, you see that we can train a model, and now we will see what we can do with this model. So let's say that we train the model, right? We see very good accuracy, we are happy, but what can we do now with this model? How can we get predictions with this model? So let's say we have a new image and we want to see, okay, this is a 5, this is a 6, what it is. So after we train the model, what we do is that we can call predict. Let's take again a batch of images. Remember, you don't pass only one image, you pass a batch of images every time. So in this case, we will take from the test images the first 10. So this is the normal slicing method for Python. So here we have 10 images, and the way we get the predictions of the model is with the predict method. So we call model.predict, and we pass the input, and this returns the model output, so the predictions. Now these predictions are 10 predictions, first of all, because we have 10 images. And each one of these 10 predictions consists of 10 numbers, 10 probabilities for each one of the 10 categories, right? So let's see what are these probabilities for the first image. So predictions 0 is the probabilities, the 10 probabilities for the first image. And it's not very helpful to see it like this. What we care about is which of these probabilities is the highest, right? To see what the model predicts. So to get the highest, the argument with highest probability, the highest number, we call argmax. So argmax will return the index of the maximum argument of this list, of this array. And we see that it's the 7th one, which is this one. So let's see what is this probability. And in order to see, we call prediction 0. So for the first 10, for the first image, we take the 7th, which is this one. And we see that it's quite high. So the model predicts with a probability score 99.92% that this is a 7. Now let's see what this means. This means that we are correct. Why? Because if we take the test labels and we check what is the first label for the first image, it is indeed 7, which means that the prediction and the label are the same, which means that we made the correct prediction. And this is how we get a prediction for a trained model, just .predict with the inputs. Now let's see how we evaluate the model. Okay, we predict the first one, but what about the rest of the images? So in order to get evaluation of the model on new data, not the ones that it has already seen during training, we call model.evaluate. So model.evaluate is a method that returns the loss of the model, the loss that we use for training, and also all the metrics. In our case, we have only one metric, the accuracy. We pass 2 arguments. The first one is the inputs, and the second is the targets. We need, in this case, the targets. We didn't need in the prediction because we might not have, but for evaluation, we need to know if what is the correct answer, right? So by running this, we can see that it evaluates, and the output is 97.9%, almost 98%, which is pretty good again. So I know it was quite fast. I know that maybe some of you might have some missing points here, but don't worry, we will see it in more details. The main idea is that just in something like 15 lines of code, we managed to build and train a neural network that takes handwritten digits and it classifies as which.
I'm sorry to have interrupted you, Dimitris. I think there are some good questions. I personally think that your insights on them would be very valuable. And
Okay.
since we reached this place where we do have the output and the prediction values, so I'll try and read out the questions, and probably you'll be able to help answer them in the interest of the curiosity that I'm seeing with everyone.
Okay.
Sure. So the first question was, it's kind of interesting. It says, how does the loss compares with the metric? Aren't these both metrics to improve the model? So I think what's being asked is, we are using a loss function and then we are also calling something as a metric. So what was the exact difference between a metric and a loss function in the context of neural networks?
Okay, I mean, so to answer this question, we need to understand some things regarding gradient descent and what we try to achieve, which actually is the target, the goal for this chapter. So I think that it's better to answer it after the completion of this presentation, because you will see actually why we cannot use metric and why we do need to use loss.
Sure. The next was, I think this would be a little simple. Why did we transform the data?
So the data, again, we will see in the next, when we will talk about tensors, what is the idea? The idea of reshaping, for example, is that tensors have different rank, different shape, and not all layers can process all ranks or tensors of different ranks. Each layer expects specific kind of input. And this is why we have to make some transformation. Now, for the 0 to 1, this is for the reshaping part. For the 0 to 1, it's just that we have noticed that it's not a good idea to feed values with great magnitude, big values to the model. It doesn't help in training. We want to normalize to something smaller. So usually we normalize from 0 to 1 or from -1 to 1, or we divide by standard deviation and subtract the mean. We will see this in the future, but we will explain again about the pre-processing in detail in the next chapters.
All right. I think there are two other questions. One is related to RMS optimizer. I think that we'll cover in the future slides. There was one question which says, what does 469 mean in the fitting? In the model slide, there was something called 469. Is it possible we can go back to the fitting slide?
Here.
In the fitting slide, yeah.
Wait, misbehaves. Okay, now it misbehaves a lot.
So I think that 469 are basically the number of steps.
469 here, yeah.
Yeah.
Yes, it's the number of steps. We will see. So we had 60,000 images divided by the 128 images per batch. It's how many batches we process, and this is the number.
And the last question, I'm sorry if I'm taking time. Why did prediction 0 have 10 values? Because there are 10 classes. When you printed the first index of prediction, it had 10 values. So these 10 values are basically probabilities of every class.
Yeah, of every class for the first image. So here we have a prediction for 10 images. 0 is for the first image. We use Python, so we start from 0. So these 10 values are for each class for the first, and they correspond to the first image only.
Right. I guess that's the main ones. Let's get back on the flow.
Okay, so let's continue. We saw how we will evaluate the model, and we saw that, as I mentioned before, it's quite easy in Keras to build and train a model. In this case, it was just 15 lines of code or something. Now, Probably there are many points that you might miss on what we do and why we do it. So let's go deeper and see what tensors are and what tensor operations are and what is gradient descent, as I mentioned before. We will start with tensors and data representations. Again, representations. So tensor is, imagine it is actually a container of data. So all the data we handle deep learning are contained in tensors. So the input to a layer is a tensor, the output of the layer is a tensor, the output of the model is a tensor, everything is tensor when we talk about data. And in most of the cases, it's numerical data. So it can be integers, it can be float numbers in different encodings, it can be Boolean values. In some cases, it can be even strings, as we will see, I think, in chapter 11. But the main idea is that what data we have, the numerical data that we feed to the model and what happens internally in the model, all these are tensors. And tensor is more or less a generalization of the matrix. So if you're familiar with what a matrix or a vector is, it's more or less this, but in arbitrary dimensions. So matrices are just two-dimensional things. Tensors can be n-dimensional. And these dimensions are the axes, as we will see right now. So let's see some examples of tensors. First of all, we start with scalars. Scalars are just numbers like 12 or minus pi or 6 or whatever, right? So these are rank 0 tensors. Rank 0 because they don't have any dimensionality, they are just numbers, plain numbers. This is an example of a rank 0 tensor. So if we call NumPy, I hope you are familiar with NumPy. It's something, a tool that we use to make fast optimized numerical operations with big data, not only numbers for NumPy and for Python. So NumPy.array12 returns a tensor with 0 axis of rank 0. And you can see it here. So this is a rank 0 tensor, just 12. And the number of dimensions, which is the rank of this, as you can see with dot and dim, is 0. So this is a simple example of a scalar, a rank 0 tensor. Let's move to something more interesting, rank 1 tensors. So the vectors are rank 1 tensors. They are just a list of numbers, okay? So here we have a list of 5 numbers. And if we pass this list to NumPy array, it returns a rank 1 tensor. And this is now not a list, but a tensor of numbers. And the dimensionality of this is, of course, 1, as we mentioned before. So this is more or less what rank 1 tensors are, just vectors. Now it's important not to confuse, because it is quite confusing, and I had discussions that I didn't understand what we were talking about among engineers. When we talk about dimensionality, so this is a 5D vector, right? Because it has 5 numbers. If it was a space, it would be the point at a 5-dimensional space. But it is a 1D tensor. So in order not to be confused with the vector dimensionality and the tensor dimensionality, we use the word rank or axis, number of axes for tensors. So this is a 5-dimensional vector, but as a vector is a 1-dimensional tensor or a tensor of rank 1, okay? So remember, vectors rank 1, no matter how many elements it has internally. Let's move to the matrices. Matrices are rank 2, like list, but we have list of numbers. So we have 2 dimensions. This is an example of a NumPy array with number of dimensions 2. And this one, I think the shape, let's see what is the shape. It's a 3x5, okay? So again, the dimension of the first axis is 3. The dimension of the second axis of the tensor is 5. But it is still a rank 2 tensor. And you can have high rank 3 or higher rank tensors, we don't care, but usually so this is an example of a rank 3 tensor, okay? Same idea as before, we have 3 as number of dimensions, and the shape of this is 3x3x5. So in deep learning, you usually use tensors of rank from 0 to 4. It's very rare cases where you will use something like rank 5 tensors, and it's for video data, as we will see some examples in the next slides. But usually keep in mind that scalars, first of all, are rank 0, vectors are rank 1, matrices are rank 2, etc. And we can have rank 3, rank 4, etc. Now, what are the key attributes of a tensor? So a tensor can hold many types of data and can be many things. We have to assign some attributes to understand what we are talking about. I already mentioned the ranking, okay? This is the number of axes we have in a tensor. The second one is the shape of the tensor. So this is how many dimensions we have at each axis. So in the last example, we had a rank 3 tensor, and the dimensions were 3 for the first axis, 3 for the second, and 5 for the third axis. And the third important attribute about the tensor is the data type. So each tensor can hold data of same type. It's not like the Python list that you can have strings and integers and floats in the same thing. In TensorFlow, you have to have that we will use, the data have to be of the same type. And even in NumPy, just in NumPy, you can have object as a type. Now, let's see what we already discussed about tensors with an example with the data we already used from MNIST. So this is again how we load the data. And now we have these 4 things, but now we know that these 4 things are actually tensors, okay? And this is the tensor that holds the train images. Let's see what is the dimensionality of this, how many axes it has. And it has 3 axes, and this is the shape. So it's 60,000 by 28 by 28, as we saw before, but now we know that what this means. This means that the first axis has 60,000 dimensions, the second has 28, and then 28. And we will see what corresponds to each one of them later on. But let's also see the data type of this tensor. So the data type for this specific tensor is unsigned integer 8. So when we divide it by 1, it's changed to float, but the original type is 8 bits. So from 0 to 255, non-negative numbers. And this is an example of how we can get for any NumPy tensor the rank, the shape, and the type of the data. Now, we saw one example of a tensor. We described more or less what a tensor is. Now let's see some real-world examples of data tensors. First of all, we will talk about the vector data. Now, I mentioned before that vectors are rank 1 tensors. You see here rank 2, you might be confused. This is because we are talking in the context of TensorFlow. And as I mentioned at the beginning, in TensorFlow, we don't feed to the model just data, one sample point. We feed batches of data. So we feed many samples. This is why always we have an extra axis at the beginning that holds the number of samples we have. For example, if we have a data set with 100,000 people, which means 100,000 samples here, and for each one we have 3 features, the age, the gender, and the income, then we have a vector data of rank 2, and it's 100,000 by 3. So this is an example of vector data. Another one could be a data set of 500 text documents. This is a bit more complicated with counts of word appears from 20,000 words dictionary. In this case, we have 500 samples, and each sample consists of 20,000 numbers. Each number represents something. In this case, represents how many times the specific word appears in the document. So these were examples of vector data, rank 2. Now let's see some rank 3 examples. What could be a rank 3 example of data? Time series. Time series are usually rank 3. So in this case, we have, first of all, the first axis, as always by convention, is the number of samples. And by convention also, the second axis, when we have time series or sequence data, is the time steps. So how many time steps we have, which means that the third axis will be how many features we have. Specific example, let's say we have a data set of stocks for the market. And we have three features, the minimum, the current, and the maximum value of the stock. And we take the time steps, we record it every minute, okay? And let's say we have the recordings for 250 days. In this case, we will have a rank 3 tensor for this dataset with 250 number of samples. 390 is for 1 day, all the time steps per minute. And 3 is how many features we have for each point. In the same similar way, we have, for example, a dataset with 1 million tweets. So in tweets, we have 280 characters, and they are encoded as 128 one hot unique characters. So in this case, we will have number of samples 1 million, number of characters in this 208, and each character has a 128 encoding. And here you can see an image of what this would do. How you can represent it. So each one of these is one sample. Each sample consists of some time steps, and each time step consists of some features. Now, this was rank 3. Let's see some rank 4 data. So images are rank 4 data, actually. Again, first axis holds how many samples we have, how many images. In the previous example, it was 60,000 training images, if you remember. Then we have the dimensions, so the height and the width, and the number of colored channels. Now, by convention, usually we use the channel axis as the last axis, but in some cases you might see first the channel and then the dimensions. And also, if we don't have 3 channels, or like the RGB or something else with infrared, in some cases we have just, like in our example, grayscale, which means just one number. In this case, it's good to hold a channel 1 dimension. So here you can see what this looks like. Let's say we have here, you can see 3 images. So the number of samples, each one has the height, the width, and the color channels. So images, again, image data, rank 4 tensors. And you can have also rank 5, as I mentioned before. So video data is a common example where we have, first of all, the number of samples, then the number of frames. In this case, let's say we have 4 video clips, so 4 samples in our dataset. Each video clips consist of 60 seconds with 4 frames per second, which means that we have 240 frames per sample. This is the second number. And then we have the dimensions, 144 by 256. These are the axis 3 and 4. And then we have the channels, which are 3 colors, because we are talking about colored videos. Now, of course, we don't always hold all this information. This is a big thing. If you multiply all this, you will see how many things you have to hold in memory. This is almost 400 megabytes. In real life, we don't hold, of course, all this information. Now, this is what tensors are. We saw what it is. We saw that it can have different dimensions, what we put in each dimension. First dimension, the samples, then whatever it is. Different examples of tensors. Now let's see what we can do with the tensors. So let's say we have this tensor. What we can do is apply some operations, some functions, okay? And the whole idea with the deep learning is that we apply simple elementary operations on these tensors, and we get something that is quite good as a result. So let's see an example. Elementary operations among tensors is all deep learning is about, and if we stack many of them, we have something complex. In the example that I presented before, the model, we used, if you remember, the keras.layers.dense layer. And what is this dense? We didn't explain before, but let's see actually now what this is. So what it is just 2 very elementary operations. One, multiplication, so dot product between the input to the layer and some matrix, some tensor. And after this multiplication, we have an addition. So this is all the dense layer is, just dot product and addition. And on this, we apply some activation. We will see in the next, why we need this activation in the next slide. But as you can see, it's just elementary operations. It's not something complicated that goes on inside the layers. Now, inside the book at this point, there are some details about the element-wise operations, like the addition we saw before, or the dot product. You can see some naive implementations of this and comparison to NumPy in speed. The whole idea is that you don't have to care about these element-wise operations because NumPy and TensorFlow already has them implemented. You can just call dot, for example, or something like this. You don't have to implement it by yourself. It's also mentioned what broadcasting is. You don't have to know this unless you write your own loss function or your own layer implementation. Tensor product, tensor reshaping. So you saw actually reshaping at the example we used. If you remember, we had the tensor 3, rank 3 tensor, 60,000 by 28 by 28. And then we had to reshape it. Why we had to reshape? Because dense layer, the one that you see here, accepts a rank 2 tensors by nature, okay? So you can, if you try to fit the rank 3 to a rank to a layer that accepts rank 2, it will throw an error. And this is why we had to reshape the tensor from rank 3 to rank 2. And the idea is that we have to hold all the data, so we multiply the last 2 dimensions and we flatten them. Now, we saw that deep learning has layers, and layers are just elementary operations on tensors. But let's see how we can interpret it in a different way that it makes more sense intuitively. So we can see all the geometric, all the operations, the tensor operations, as some point, all the tensors, first of all, at some point in some geometric space, okay? So imagine a vector with 3 features. It can be, as we saw, the age, the gender, and something else, salary. No matter what it is, actually, we can see it as a point at some space, in 3D space in this case. Which means that if all the tensors are somehow something, some points in a geometric space, then the tensor operations have some geometric interpretation, are some transformation in this geometric space. Let's see a very concrete example. Addition. So addition is nothing more than the translation, the movement of an object in space. And it's just movement, meaning that we don't distort the object. For example, if we have a point A and we add another point B, what we do is that we just translate, we just move this point. Now you cannot, of course, distort a point, but let's see what it means for an object. So let's say we have this image, okay? And then we add a vector. So this has a geometric representation of moving this object horizontally and vertically. So you see that addition has a very clear geometric representation with interpretation, which is translating, moving an object. Another example would be rotation. So we saw at the first chapter that we could rotate the axis, okay? So rotation, again, is a very simple multiplication. So if we multiply our object with a specific matrix, we just rotate this object. In a similar way, we can scale it, or we can do many things just by multiplying or adding values to an object. And all these transformations are linear transformations, affine transformations. This is just a fancy way to say that if we have lines, we preserve the lines. So if this is a line here, it will remain a line, it will not become a curve. And that we also preserve the parallelism. So if this is parallel to this, it will remain parallel. However, the distances and the angles can change. It's not important what I mentioned right now. It's important to remember that all these affine transformations are actually simple transformations in some geometric space. Okay, it can be of any dimensionality or any structure, but it is some kind of geometric representation. Now, why it's important to mention this? First of all, I mentioned the affine transformations. Affine transformations are very good for what we want to do, and we will see why, but they are not that good. The problem with affine transformation is that if you have many of them applied on a tensor, it's like having only one of them. What I mean by this, so let's say that we have a tensor, okay, x can be this or whatever. And then we apply an affine transformation, affine one, whatever it is, we don't care. And then we apply at the result another one, affine two. Now you could think that these are two different transformations, right? Actually, it's one. I mean, this is the result. Again, affine transformation is just multiplication and addition. So we multiply x by w1 and we add b1. And then we take this, we apply the second affine transformation, we multiply by w2 and we add b2. But if you break this down and change it a bit, you will see that it's just one affine transformation. We multiply by w2 dot product w1 and we add this. So the idea here is that if you have multiple dense layers, like here or in our model, without an activation, then it's the same as having one. So we don't go deep. So the whole idea is to have many steps of simple transformations. But if we don't have any activation and we just have affine transformations, it's just one step. It's like this. And this is why we used that word, the activation, okay? So activation is very important in order to break this linearity, in order to break this feature. So if you have multiple dense layers, but with activation function, which breaks the linearity, then this is not the case that it's like having one. So what activations let us do is that we can implement very complex non-linear geometric transformations. So instead of having only one geometric transformation, we can build upon this. And the result is that we have a much richer hypothesis space to search for the solution. Here is, for example, Relu. As I mentioned before, Relu is just you take all the negative numbers and you turn them to zeros. And here is what we do. We apply some transformation, some affine transformation, and then we apply this non-linearity. You can never have this cut just with, no matter how many affine transformations you will apply. This is why we use the activations. And let's see what we can manage with this. So a geometric interpretation of deep learning now, not of the layers. So the idea is that deep neural networks are just layers, are just chain of tensor operations, like the ones we saw before. And each tensor operation is just a simple geometric transformation in some space, right? Like moving, rotating, scaling, etc., with the nonlinearities. Which means that the neural network is actually a very complex geometric transformation in some high-dimensional space. What would this mean with a simple example? So the example in the book is that imagine having two pieces of sheets, so one red sheet and one blue. And then you take them and you crumple them together in a small ball, okay? So you have this small ball with blue and red sheets, and this is your input data. And your target is to uncrumple it. So what you try to do is to find some geometric transformations that will uncouple this ball and make the two classes cleanly separable again. And here is an example of what this would look like. So the idea is what us humans would do in this case. So we would open this, unfold this, pull this. So we would apply this small step-by-step incremental transformations on this ball so that we try to unfold it, to decompose it. And this is actually what the deep neural network tries to do. It tries to do incrementally decomposing a complicated geometric transformation into a long chain of elementary ones. So instead of having this whole thing to unfold once, we break it into steps and we try at each step to learn what exactly movement transformation we try to do. So this is an intuitive idea of what these layers do. They try to apply this kind of transformations. But the question is, okay, let's say that they can do it, but how do they know exactly how to rotate, how to scale, how much? The idea is that we need to parameterize this transformation to make the correct movements, right? And how we do this? So this is where gradient-based optimizations comes in the scene. Now, for the dense layer that we saw before, remember with two dense layers, we managed to classify the digits, right? So they are quite powerful, but what they are just multiplication and addition. The idea is that at the beginning, these parameters of this transformation, the dense layer transformation, are just random weights, okay? If we manage to tweak this to make something meaningful, it will get a result that is good. Now, this WMB contains the information learned from the training data. So what we try to do is change WMB to make some sense. At the beginning, as I mentioned before, WMB are randomly initialized, which means that this output that you see here is more or less meaningless. It's just random numbers. So the goal is to change this W and this B so that when we pass a specific input to take the necessary, the target output, okay, or as close as it can be. And this is a training process. So this gradual adjustment of these weights is what we call training process. Now let's see what is this training process. The training process consists of this, let's say, simple 4 steps, and we do them together again and again in a loop. First of all, we have the data and we get some patches. Okay, so let's say 128 images from the training data. And we get both the images and the targets, the Y true, let's call it, the labels in our case. Then we take this batch of training samples and we run them through the model, and we obtain some output of the model, the predictions, let's call it Y-pred here. The third step is to take the Y-pred and the Y true and compare them. Again, remember, we have the loss function. The loss function is just a function that takes these two things and outputs a number. And the number, the smaller it is, the better it is. It means that these look alike. So what we try to do is minimize this number, this loss. And in order to minimize, the only thing we can do is to change the weights, right? So what we try to do is to update all the weights of the model in a way that it slightly reduces this loss on the plot. Now, the first 3 steps are quite easy, but the fourth is not very clear. How do we change the weights, right? So we have a loss, let's say 3 or whatever, we don't care. What we care about is how we change the weights so that it becomes smaller. One idea would be to change them one at a time. So let's freeze everything, choose one coefficient, one number, one parameter, increase it a bit, run again, get the loss. If the loss is higher, now we have to decrease. Decrease a bit, run again, okay, it's good. We freeze it, we unfreeze it now. But the problem is that we have millions of them. We have millions of parameters. We cannot just do it, it's not efficient. The good thing is that there is a solution, and it's called gradient descent. So let's see what is this solution. In order to understand this solution, we have to understand some other things first. One of them is that the word differentiable. Every function that you will use in deep learning for the layers and the loss has to have this, this feature, to be differentiable. This is a fancy word to say that the function has to be smooth and continuous. So you cannot have gaps and you cannot have very itchy angles or something like this. This is an example of a differentiable, a smooth and continuous function. Okay, let's say we have sent to be x plus y. So let's say that y is our input, x is the input, y is a parameter. The good thing with these kind of functions is that, as I mentioned, since they are smooth and continuous, small changes in y produce small changes in z. You will not jump to another point. You will go at this area, okay? And in this function, we also know that if we want to decrease z, what we have to change in y? So do we have to increase or decrease y? We know this thing in these kind of functions. And it's the same for the model. So in the model, since we use only differentiable functions, small changes in the coefficients, in these parameters, produce small predictable changes to the loss. and the important word here is predictable. So the tool to do this, this tool, the gradient and the gradient descent, it allows us to change all these coefficients, all these millions of coefficients in a single update altogether. We don't have to change them one at a time. So gradient actually what it does is that it describes how the loss varies as you move the model's coefficient in different directions. The same way that we know that if we move it a bit higher or lower, how Z will change. The same way gradient describe how the loss in our case varies as we move these coefficients. Now, let's see how this is done. But before we understand how the gradient works, we have to understand another notion, which is derivative. And this is very, very important because it's actually very powerful. And we are happy to have this actually. And we have it already implemented. So let's say we have a function f of x equals y, okay? And it's continued and smooth. We already said that we need these two. Now, what does continuous mean? It means that, as I mentioned before, small changes in x produce small changes in y. So if we make a small change epsilon x and we move x a bit to the right, if this is small enough, we can approximate f, so how y will move, as a linear function, as a line, okay? So very locally, if it's continuous and smooth, then locally, this curve looks like a straight line, okay? Which means that we can write this f as a function, as a linear function, as a function of a line with one coefficient, a. Now, this a is called derivative. So all derivative is just this number that is the slope. Okay, imagine a as the slope. This is a good picture. So we have this this curve, this function, and we have this point x0. So this a is just how many degrees is the tangent at this point. And why we care about the tangent? I mean, okay, we have the slope, so what does this mean? What it means is that we know which way we have to move x in order to decrease y. So if we have this kind of slope, it means that the right way, x will decrease, and the left way, y will increase. And this is very useful because in this case, of course, you can say, yeah, I don't need the slope. I see this is a minimum. I can go directly to this x and this is a minimum y. But what if you didn't have this black curve, okay? Imagine that you don't see the curve, you just see this point. If you have this point and you don't have the slope, you don't know if you have to move right or left, how much you have to move in order to decrease y. The information that is behind this slope, this derivative as it's called, is it shows you which way you have to move in order to decrease y. So if you want to reduce the value of fx, you just need to move x a little in the opposite direction of the derivative, in this case, right. Now, the derivative is the slope when you have one x, one coefficient, one parameter. But in our case, we have many, we might have millions of parameters, right? So the good thing is that we can take this derivative for all of them. So it's called gradient. This is what gradient is for each coefficient, each parameter, what is the slope? How do we have to move in order to decrease the loss in our case? So as I mentioned, for a scalar function, the derivative represents the local slope of the curve. The gradient of a tensor function represents the curvature of the multidimensional surface described by the function. Let's say before we had an arbitrary f of x equals y, okay? So it's not, why do we want to reduce y? We might want to increase. But in this case, we have something tangible. So as we mentioned before, we have a dot product of some input we have with some w, okay? W has the coefficients, the parameters. We obtain y prime. And then we pass y prime to the loss function, y prime and y2, and we get the loss value. Remember, all we try to do is reduce this loss value. The good thing is that these two lines means that we have the third line, which means that the loss function is actually just a function of W, of the weights. And since all the operations that we apply are differentiable, this means that we can get the gradient of the loss with respect to the weights. And again, the gradient indicates the direction and the magnitude of the change in loss value when we modify all these coefficients, which means that for all these millions of numbers, we know now with the gradient, we don't know how to calculate the gradient. Don't care about this. We just know that we can get the gradient of the loss with respect to the parameters. And the gradient, again, is the partial the derivative for each one of these parameters. And the derivative shows us how we have to change this to reduce the loss. So this is why we use a loss, and this is why we don't use a matrix. The difference between the loss and the matrix is two things. Actually, it's one thing. It's that the loss has to be differentiable. Metrics don't have to be. Metrics is just whatever function we want to apply between the y pred and the y true to get something that makes sense to us. Loss has to be differentiable because we need to be able to calculate the gradients. This is the reason. And because the gradient is all the information we have to know if we have to increase or decrease the coefficient, each coefficient. So let's see the previous 4 steps in more detail. Actually, the fourth, because the first 3 are the same. This is the stochastic gradient descent algorithm. Again, first we draw some training samples, X and the target Y true. We run the model on X, we get the predictions, Y pred. This is called the forward pass. Then we compute the loss for the whole batch, and we measure the mismatch, how different is the Y pred and the Y true. And then, since we have this loss, which is one number, we can compute the gradient of the loss with regard to the model parameters. And this is the backward pass. And since we know the gradient, all we have to do is to move to the opposite direction of the gradient, of the slope, okay, to decrease. So we take all the weights that we have and we decrease them. So we just subtract from the previous values the gradient. And we can multiply actually with a scalar, a number, let's say 0.1, so that we make smaller step or bigger step, okay? So this is what it is. This is what gradient descent is. And here is are 2 images to show how this works. So let's say we are here, we know that in this point, because again, we have differentiable function, we know that the derivative here, the slope is like this, okay? Which means that we have to move right. So we move right, how much? Learning rate, this number will say how much, because we multiply this by the gradient. And we move to the opposite direction, we get here. Again, we take the slope, the gradient, move here. We take the slope, move here. So if we have not one, but many parameters, this is, for example, if we have 2 parameters, how this will move. Again, at each one of these points, we calculate what is the slope at this specific point, which means that we know how we have to move, which direction we have to move. Now, we saw that if we have the gradient, we can calculate the gradient of the loss with respect to the parameters, and then we can tweak the parameters. The question is how we get the gradient. And again, we are very lucky because TensorFlow has a tool that for automatic differentiation to get the gradient automatically. We don't have to care about this. In the past, we did have to care about this, and the author describes how painful it was back then. So again, we are very lucky. We have gradient tape, just one tool that keeps record of all the tensor all the operations that are executed for this differentiable big operation. And this means that we can retrieve all these slopes, all these derivatives, so the gradient. And this is how it works. So this is a very specific example of how we get the gradient. So we import TensorFlow. Let's say we construct an input, x, just a number. And then this is how we open the scope. So with tf.gradient tape as tape, this is a way to open a context in Python. a scope, and everything that happens inside this context, in this clause, is recorded by the tape. Okay, so all the operations we need the gradient from have to be inside this scope. Here we have a very simple chain of operations. We have a multiplication and an addition. And let's say now that we want to get the gradient of y with respect to x. Okay, all we have to do is take the tape and call the gradient method. The gradient method takes two inputs, two arguments. The first one is the element that you want to get the gradient of, and the second is with respect to what. Okay, so in this case, if we want the gradient of y with respect to x, we call this thing. If we run it, we see that it returns a tensor, TensorFlow tensor. Shape is empty because it's rank 0, if you remember. We get the D type, and the important thing is that we get the actual gradient at this point. This means that for this function, the differential function, at this point of the function, at point 0 for x, this is the slope, which means that first of all, it's positive. So if we want to increase y, we have to increase x. And it also means that in this area, if we increase x, y will increase twice, so 2 times. And for this actual function, it happens not only close to 0, but everywhere because of the nature. So this is what it is. This is how you get the gradient. The good thing with gradient tape is that it doesn't work only with scalars, it also works with tensors. Otherwise, it would be very helpful. Yeah.
Dimitris, do you think it would make a little bit of sense here if we can actually, if I, with your permission, if I really write what that differentiation would look like of y is equal to 2x plus 3, with saying dy by dx is this 2.
Can you, I couldn't hear very clearly. Can you
I can actually annotate how that mathematical function really looks like on the screen. If that helps the other people to really see why it is coming out to be 2.
But I mean, you could take the derivative of this, and it's just a simple formula. This part doesn't matter; it's 0, and this part is because we have multiplication. It's 2. The thing and why we don't show this, I thought of, okay, let's show how it's done mathematically, and then show that it is correct by gradient tape. The whole idea is that to show that you don't even have to know how to differentiate these functions, because okay, in this case, it will be just a simple operation, okay, a simple chain of 2 operations. In the actual model, it will be millions of operations. The good thing is that we don't need to know how to compute the gradient.
Yeah, okay.
So, as I mentioned before, it works not only with operations on scalars, but with operations on tensors too. So let's see an example. We have a variable, now it's a tensor of rank 2, and we have this computation inside the scope of tape, which means that we can take then tape.gradient of y with respect to x, and we can get the result. And the result is again a tensor, but this time we have the slopes, the derivative, the partial derivatives of each coefficient of our variable, which is again very powerful. We don't have to compute anything, it just returns what is the slope. And of course, it doesn't work only with tensors, but also with lists of tensors. So in this case, let's say we define 2 variables, w and b. This is actually what happens in the dense layer. And we have the input x. So let's say that the output of the layer, of the operation, is the matrix multiplication between our input and this tensor, and we add this tensor. And again, we need to know how we have to change the numbers in these 2 tensors to decrease the loss, right? So what we have to do is take tape.gradient and pass not 1 tensor, but a list of tensors here. And we just have a list of gradients. So we have a list of 2 gradients of 2 tensors. This is the gradient for the first tensor for W. This is the gradient for B, for the second one. Now, this is how gradient works. And let's see how we can use this knowledge, this new knowledge, on our first example. So let's go back to the beginning, get the data, reprocess the data, simple MNIST as you remember it. Then we have the model. We define the same model as before, sequential. We have two layers. Dense layer 512, dense layer 10. Here we have activation Relu and activation softmax. Here is what is going to happen. We will get batches of input data. We will pass them through the layers. We will obtain the prediction Y and compare it to the target Y with the loss function. We get the loss score. And then what we try to do is to decrease this loss score. How? By changing the weights. So the optimizer will take the loss, will compute the gradient, and will change the weights based on the gradient. It will go to the opposite direction. So it will subtract the gradient, multiply it by some learning rate. Now, let's compile. We will use again some optimizer and the same loss function as before. We will fit it. We see that it fits. So nothing new here. This is exactly how we started the session. Okay, now let's re-implement all these steps, but without Keras, just plain scratch from scratch with TensorFlow. In order to do this, we have to define some things. First of all, we have to define the dense layer. Okay, so let's write a function that does this thing. Is a layer that will apply dot product between any input and our weights, and will add a biases, another number. And the output of this will be passed through the activation and will be returned from the layer. Here is the code of how to do this. So we define naive dense. The constructor will take the input and the output size and whatever activation we want to apply afterwards, and we assign the activation. We compute the shape of each one of the two variables, so the W shape and the B shape. This is plain linear algebra. This is input by output, the tensor. This is vector, so output size. We initialize these variables with some numbers. So here we pass random numbers from 0 to 0.1, here just zeros, and we create the variable. So self W will be this variable, self B will be this variable. And this is where everything happens. So whenever we call this naive dense with some inputs, what we will do is that we will matrix multiply these inputs with self W, and we will add to the result the self B. And then we will apply the activation, this self activation, and we will return the output tensor. We also define a property for the weights, which is just a list of the two weights, the self W and the self B. Now, since we have defined the dense layer, the naive dense layer, we can actually define the model to use it. Okay, so naive sequential. As you remember, sequential takes a list of layers. So we will do more or less the same thing here. A constructor with a list of layers, we assign it here. And this is all we do. So every time we call the model on some data, on some inputs, we assign the inputs to X, and for each layer, we call the layer on this data, and we assign to X, then we pass X to the next layer, the output, next layer, etc. And in the end, we return the output tensor of the last layer. And again, we create a property here, a method for returning the weights, which is just a list of the weights of all these layers. So for each layer, we extend the list with these weights. Pretty straightforward. So now that we have defined this naive dense and this naive sequential, we can actually build a naive model. So the way to build it, we call naive sequential. Again, it takes a list of layers. We pass two layers, one naive dense, this is the input size, the output size, and the activation Relu like before. And here we have the input size to be the same as the output of the previous. The output size will be just 10 numbers, and the activation like before will be softmax. And we make sure that everything works correct. We have 4 weights when we call model.weights. let's write read a short generator. So this is just a class that will return batches of data. You remember we have to break the data to batches. So we pass all the images, all the labels, and how many we want per batch, and the batch size. We just assign them, and we compute, okay, how many batches. So this is the number 430, whatever it was that you asked about. So this is just how many images we have divided by how many per batch. And every time we call next, so in a for loop, this generator, it will return a batch of images. So it will just take self images, all the images, and will return from where we were last time to where we were plus 128, and the same for labels. And of course, we have to increase the index by batch size so that we move to the next batch. And this will return the labels and the images. So pretty straightforward Python code. Let's see what will happen in the train loop. So we have defined the model, we have defined the generator for the data. Now we have to define what was feed, if you remember. What we want to do is to compute the predictions of the model for the batch, the images in the batch. When we have these predictions, this y-pred, we want to compute the gradient of the loss. So we compare it to the y-true, we get the loss, and then out of this inside the tape context, and then we compute the gradient. And after we have the gradient, we move the weights of all these parameters by a small amount in the direction opposite to the gradient, as we explained before. Okay, so this is actually how we do this. We have the one training step function, takes the model and the batch. We open the scope with tape, gradient tape, and we compute the predictions, the output of the model on this batch. And then we compute also the loss. So we use again the same loss as before, sparse categorical cross entropy. We pass the labels of y-true, the targets, and also the predictions of the model. So this will return the loss for each sample. Okay, so we have, let's say, 128 numbers here. Then we want to reduce it to take one number as output, and we can do this with tf.reduceMin. So this will return one number here as an output. And the next thing we want to do is, since we have the loss, to compute the gradient of the loss with respect to the weights of the model. So this is what we do in this line. We say that tape.gradient, and we want the gradient of the loss with respect to the model weights. Remember, this is a list, and we saw before that we can pass a list of tensors to compute the gradient for. And after we have the gradient, we can update the weights. We have not yet implemented this step. We will implement. Python, for some reason, allows us to use it here. So we get the gradients, and we pass the gradient, we pass also the model weights, and we will use this function. And of course, we want to get the loss, this average loss, this number, to see if it trains or not. So let's define it and move. Now, you saw that we had the function that we didn't define of how to update each weight, okay, given the gradient. So the idea is that we want to, for each weight, we want to subtract the corresponding gradient. And we usually multiply it by a factor to make it a bit smaller, to make small steps. So this is more or less our optimizer. So when you hear optimizer and you imagine something fancy, usually it is something fancy, but this is a very, very simple optimizer. It gets the gradient, takes the gradients and the weights. We define the step, the learning grade. And for each pair of gradient and weight, it takes the previous weight, and in place, it will subtract from the previous weight the gradient, multiplied by this small number for a small step. This is all that backpropagation is. We get the gradient and we subtract it from the previous weight. Now, you almost never don't write your own optimizers. Never. So we will also use the an optimizer that is defined, the SDD, stochastic gradient descent. But again, this works. We can train a model with this it will work. I have tried it. And the way you call this step, if you have an optimizer object, is by calling the apply gradients method. And here you pass these pairs of gradients and weights. So now that we have defined everything, let's define the fit function. So fit will take the model, all the images, all the labels, how many epochs, and the batch size. And for each epoch, it will create the generator. We have to create because it will not have to return something with the next function otherwise. And for as many batches as we have, we call next at every step. So batch the generator dot next will return the next batch of images and labels. And we pass this to the one training step that we already defined with the model, and we obtain the loss. Remember, inside here, we already have the step where we update the weights. And we just print the loss every 100 batches. So let's see what will happen if we run this. The first lines, just what we did before, we load the MNIST dataset and we pre-process it. This is the line that makes everything work. So we call this function, we pass the model, all the train images, all the train labels, how many epochs and the batch size, and magic happens. Let me go over. So what we see here is that it actually works. So this is a loss, okay, for each batch. We start with a very high loss, 7, and it starts decreasing, 2.2, 1.9, 1.6, 1.5, 1.3, 1.1, 0.9, 0.9, 0.8, we reach 0.74, even 0.61 at some point, okay? So what we already implemented now works. Let's see, let's evaluate the model. So in order to evaluate, we cannot call dot predict. We haven't implemented in naive sequential this. We can just call the model. So we pass the images, the test images this time to get the predictions. Since this is the output of the model, it's a TensorFlow keras. It's a TensorFlow tensor. So we have to get like this, the NumPy tensor. And since now it's a NumPy tensor, we can call NumPy argmax. So here, instead of having 10 numbers, 10 probabilities for each image, for each one of the 10,000 images, we will have the argmax, so the number, if it's the third one with the highest probability score, the fourth one, whatever it is. And these are just the numbers. So what we want is to see how many we got correct, okay? How many of these numbers are the same as the labels. So if we predict 7 argmax and the test label is 7 plus 1. So this is just a binary tensor. And if we get the average, we get the accuracy. So we have, with what we implemented right now, accuracy 82%. I know that it was quite fast. I know that there are many things that I described, and maybe you have to review the video and the chapter in the book to understand, but this is all deep learning is. We just have the layers, we combine the layers, we make the forward pass, we take the prediction, we compute the loss, we get the gradient, and this is a very important step, very powerful, and given the gradient, we update the weights. So let's summarize what we have learned and then pass to the questions section. What we learned about the tensors. So tensors, again, are very fundamental, are the foundation of the modern machine learning systems. And the tensor operations is what makes all this able to happen. And we can think of them as geometric transformations of the data. So the deep learning models consist of chains of tensor operations. And these operations are parameterized by some weights. And in these weights and the structure, of course, of the model is the knowledge of the model. So when we train, we just change these weights. So the learning is the finding of a set of values for these weights that minimize the loss function. This is all the training does. It tries to change the weight so that we have the minimum possible loss. So during training, during the learning, we get batches of data samples and targets from the training data. we compute the loss, we compute the gradients of this loss with respect to the weights, and we change the weights a bit to the opposite direction of the gradient. And what I just described is the mini-batch stochastic gradient descent algorithm. So learning this process is actually possible because all the tensor operations, as I mentioned before, in the neural networks and the loss function are differentiable. And this allows us to map the current parameters, the current weights, and the data, but to a gradient value for the loss. And this is what the backpropagation is, how to use the gradient to update the weights. And we also talked about two things, the loss, which is again the quantity we try to minimize, and the optimizer, which is given the gradient from the loss, how we update the weights. In our case, we just subtract a bit of the gradient. In other cases, you use momentum or something more complicated. So it was a big, more than 1 hour and 2 minutes. Thank you very much. This was the end of the presentation.